I have here a ball. You may call it a balloon, but I call it a ball because there's no helium in it. And this ball weighs approximately 34 grams. So let me erase some here because I want, yeah. So we know the mass and we know the radius. The mass is about 34 grams and the radius is about 35 centimeters. It's about 70 centimeters across. I can calculate what the terminal velocity is. A better name would be terminal speed. I know I'm definitely going to be in this regime. So I know the mass. I know C2, which in air is 0.85. I know the radius and I know G. And so I find about 1.8 meters per second. So if I drop it from a height of 3 meters, which I'm going to do, then you would think that the time that it takes to hit the floor would be about my 3 meters divided by 1.8 meters per second, which is about 1.7 seconds. That's not bad. That's not a bad approximation. However, it will of course take longer. And the reason why it will take longer is that the terminal velocity, the terminal speed, is not achieved instantaneously. With the ball bearings, it was within 9 milliseconds. I can assure you that here it will take a lot longer. Now, if you want to calculate the time that it takes to get close to the terminal speed, that is not an easy task, because you are going to end up with a nasty differential equation. You're going to get mg, you're going to get the acceleration, which is the result of, let's go which equation we have. You see we have ma equals mg, and then we get minus the resistive force. And the resistive force has a term in v and has a term in v squared. You see, v and v squared. And so this cannot be solved analytically. But I've asked my graduate student Dave Pooley, who is one of you instructors, to solve this for me numerically. And I'm going to show you the results that he prepared. Here's a nice view graph. And you can see the effect of time on the ball if you drop it from 3 meters. Here it is. All the numbers are there. This is on the web, so don't copy anything. You have the values for C1 and C2 are given at the top. You may not be able to see them from your seat, but they are there. And what you see here is the height above the ground as a function of time. This is 1 second, this is 1.5 seconds. This is the 3 meter mark. If there were no air drag, remember we dropped an apple early on from 3 meters, it will hit the floor at about 780 milliseconds. However, with the air drag, it will be about 1 second later, more like 1.8 seconds. So the 1.7 wasn't bad, as you see, but if you look here at how the speed builds up as a function of time, you see it takes about 3/4 of a second to build up to that terminal speed, which is the 1.8 meters per second that you have there. And needless to say, of course, that the acceleration due to gravity does not remain constant, but goes down very quickly. And when the acceleration approaches 0, then you have terminal speed, and then there is no longer any change in the velocity.